All right. Hello, Science 9. Today, we are going to be talking about power. In particular, we are going to be talking about electrical power. Okay. So, power is the rate of change of energy. Okay, so this is how fast is the energy changing in your electrical circuit or in your electricity, right? So when we talk about power and the rate of change of energy, the symbol is P, P for power. But the unit is not, it's not super obvious, but the unit is basically joules. Joules are your energy per second. Okay. And a joule is also another way to calculate energy. So instead of calling it every time joules per second, because that would be a mouthful, we call it the watt. W-A-T-T, the watt. And we use a big W. You may recognize this word. It pops up on light bulbs all the time and on appliances and whatnot. So you may have already seen this word and just not known where it goes, but it basically tells you the rate of change of the electrical energy. So in other words, it is the amount of energy changed into other forms per second. So again, so this is how much, say for example, the light bulb, how much energy is being transformed from electrical energy into light or heat every second. Okay, so an example would be if you had a 100-watt bulb, that means it changes 100 watts of energy into light and heat. So you do get both per second. Okay, so that's great. So we have this thing that deals with joules per second, and we've got this new unit called watts. How do we find it? Okay, so how is it calculated? It's actually pretty easy. Power in watts is equal to current, and we want to keep it in amps, times voltage in volts. So what ends up happening is we get kind of another similar Ohm's law type of formula here, where we, instead of having V equals IR, we now have P equals IV. And then similarly, we can make our triangle P, I, V. Okay? Again, we can rearrange all this, right? So if we want to find current and we know power, voltage, we can do all that because we've got our triangle of science. Okay, so again, what is a power setting? So again, you'll notice on those light bulbs like I was talking about, you'll see 40 or 60 or 100 watts, right? Even your hair dryers or something, right? So these numbers that they put on things like that, that is called a power rating. And then why does this matter? Why do they want to tell you this information, right? It's because, so information is given. Let me just pull this down a little. So that we don't overload the circuits at home. And if you've ever had the experience where a breaker goes off and everything shuts down, right? It is likely that because the power rating or the total power rating of all the appliances on that circuit or breaker was too much. So the breaker goes, and then breaker is a switch, and it opens the circuit so that it doesn't run anymore, and then it prevents it from overloading and overheating and worse stuff happening, right? So that's why we have this, okay? And again, power equals IV, and then we can also determine power because we're talking about how it was energy per second. So power is also, again, energy per second, right? So E per T. So sometimes you can be given energy in joules, and then you can just divide by time, and you can determine how much power you have. Okay, so what does that actually look like? Okay, so let's do some calculations here, some practice questions. Okay, so for example, if I have a circuit at home, and it draws 120 volts, and I have maybe 330 amps. That's a lot, but say I have got 120 volts and 30 amps at home. So what is the power? Well, the power would then be equal to 120 times 30, which equals 3,600 watts. It's very common for people to talk about a kilowatt because of how big these numbers get. It's easier to just write kW instead of all the extra zeros. But we're just going to stay with this, okay? So, for example, we have 3,600 watts here. Now, if something said that it had a power rating of 20 watts, and I wanted to plug it into a 60 volt circuit, how much current would be flowing through there? Well, in that case, you would look at your P equals IV, or your triangle of science, and you would cover the I, and you would see that we need to do I equals P over V, which equals 20 over 60. So our I in this case would be 1/3 of an amp. Okay, 1 over 3. Okay, and again, we can talk about the energy stuff too. And these formulas are pretty straightforward, right? They're just like, V equals IR, P equals IV, or P equals E over T, or you can rearrange that to, it can also look like this. We'll make the triangle signs for that one too. Right? So as long as you have those three triangles, everything's pretty straightforward. So I could talk about something that's like, say you have, if I calculate that I've got like 80 or like 800 joules of energy, if I somehow calculate this running through my circuit every 10 seconds, right, then my power would just be 800 over 10, which equals 80 watts. This is actually pretty realistic for a light bulb. A little bit on the higher end, but it is realistic. Okay, or alternatively, I could say that I have a 20 watt light bulb and I plug it in for a minute, which is 60 seconds, then how much energy was transferred in that time? Well, in that case, we would do E equals 20 times 60, which is 1200, and this is in joules. Okay. All right, so again, we have power, and power is the rate of change of energy. We calculate this through P equals IV, and we can get this information from our appliances by finding their power ratings. With those power ratings, we can determine a whole bunch of other things, like trying to find power based off of voltage and current, trying to find current based off of power and voltage, or we can use time and we can determine the actual amount of energy, okay? So there's lots we can do with this stuff. Bunch of practice here. This is our last lesson for the unit, okay? So we're all done after this. If you have any questions, please let me know. Take care.